Welcome students. In the previous videos, we have seen about cubic structures. Okay, and how to determine lattice constant A. Okay, theoretically. Then we'll compare it with experimental values. Okay. Now, uh, now I want to find out atomic density. Means you take any 1 cubic centimeter of any solid. Approximately how many atoms will be there per unit volume. It can be per centimeter cube or per meter cube or per millimeter cube, whatever it is. Okay, usually we calculate for centimeter cube because we don't deal with the atoms which are cubic meters of solids. Okay, right? Whatever sample we take for experimental purpose, right? It will be in few centimeters only. So usually we calculate per centimeter cube. If you are interested, you can same extend the discussion for per millimeter cube or per meter cube also. Okay, so how many will be there? How many atoms will be there per unit volume? Okay, per unit volume in a solid I want. So I'll start with the simple cubic crystal where the atoms are present on the corners of the unit cell only. Nowhere else you will find any atoms. Okay. In the very beginning of the study of crystal structure, we have seen that in simple cubic crystal, number of effective atoms present per unit cell is equal to, right, from each corner atom I'm getting only 1/8. Okay, like that there are 8 corners and 8 atoms, right? So 8 into 1/8 is equal to 1. Effectively, a unit simple cubic unit cell, right, contains only 1 atom. Okay, now say A is the lattice constant of that unit cell. Means side is A, height is A, breadth is also A. So what is volume of the unit cell? Volume of the unit cell will be A cube in whatever unit, centimeter cube or angstrom, whatever it is. Okay. Now in A cube volume of that solid, simple cubic solid, okay, how many atoms are present? 1 atom is present. Okay, so A cube volume contains 1 atom. Okay, 1 centimeter cube or 1 meter cube contains how many atoms? Okay, how many atoms? That is 1 by A cube into 1. Okay, what is this 1? 1 is the number of atoms present per unit cell. Because we have started with the simple cubic unit cell, I am putting 1 here. If it is BCC, if it is a BCC crystal, okay, right, one more lattice point will present at the body center. So number of lattice points per unit cell is equal to 1 plus 1, so 2. Okay, if it is FCC crystal, in FCC crystal, we don't have this BCC lattice point, body centric lattice point, but there will be 6 additional lattice points present at the center of each face. So we have already seen effective number of atoms per unit cell in FCC is 4. So, right, in general, I take this as N. In general, I take this as N. Okay, if there are N atoms per unit cell, right, the volume atomic density, number of atoms per unit volume will be N by A cube. Remember this formula, N by A cube. Okay, now I'll show you one calculation, simple calculation, how to proceed, okay, with the practical value. In a simple cubic or in BCC unit cell, okay, let's start with BCC. In a BCC unit cell, lattice constant A equal to, right, 2 angstroms. Find the number of atoms per centimeter cube. Okay, per centimeter cube, how many atoms will be there? So a cubic crystal, a body-centered cubic crystal, lattice constant is A equal to 2 angstroms, right? He is asking us how many atoms will be there per centimeter cube of that solid. Okay, so how do I proceed? Okay, N by A cube. Okay, N by A cube is a formula which we are supposed to use. So number of atoms, okay, number of atoms or lattice points per unit volume. Okay, per unit volume is equal to N by A cube. For BCC, N equal to 2. A is, he has given it as 2 angstroms. Okay, 1 angstrom equal, because we are talking about per centimeter cube, number of atoms per centimeter cube. Okay, number of atoms per centimeter cube we are talking. Okay, so I'll convert these angstroms units into centimeters. 1 angstrom equal to 10 to the power minus 8 centimeters. So, right, A equal to, right, 2 angstroms. So it is 2 into 10 to the power minus 8 centimeters whole cube. Okay, that is nothing but 2 by, right, 2 into 2 into 2. That is 8 into 10 to the power minus 24. 10 to the power minus 24. Okay. That is equal to this 10 to the power 24 minus 24 goes up and becomes plus 24. 2 by 8 is nothing but 1 by 4. 1 by 4 into 10 to the power 24 atoms per centimeter cube. Okay, 1 by 4 is nothing but 0.25, or I'll write it as 2.5 into 10 to the power 23. Okay, right? 10 to the power 23 atoms per centimeter cube. Atoms per centimeter cube. Okay, this is number of atoms per centimeter. That's why we say a cubic centimeter of any solid approximately contains 10 to the power 22, 10 to the power 23 atoms. 10 to the power 22 and 10 to the power 23. If we ask for per meter cube, all thing you have to do is what? Instead of taking 2 into 10 to the power minus 8, 1 angstrom equal to 10 to the power minus 10 meters. Okay, so 2 into 10 to the power minus 10 whole cube, you will get roughly around 10 to the power 28 or 27 atoms per meter cube. Okay, so now remember, whenever you see any solid, it's around 10 to the power 22, 10 to the power 23 only. Okay, 10 to the Avogadro number, close to Avogadro number. What is the Avogadro number? 6.023 to 10 to the power 23 atoms per gram mole. A gram mole of some substances will be in few centimeters cube only. Okay, right? I mean, talking about solids. So this is known as volume atomic density. Next one, we go for planar atomic density. I told you crystal structure is evaluated using X-ray diffraction techniques. Means I'll send a beam of X-rays, because atoms, the size is about few angstroms, 1 angstrom, 2 angstrom, 3 angstrom. Size of any atom is about few angstroms only. Right? In order for the radiation to get scattered properly, the wavelength of radiation should be less than the size of the target. Okay, for proper scattering. Okay, for proper diffraction or reflection, whatever you take. Okay. Right, so the wavelength of light tube should be less than 2 angstroms, 3 angstroms. Means which rays are suitable, right? Electromagnetic radiation of wavelength 1 angstrom, 2 angstrom, or 0.5 or 0.1 angstrom. They are known as X-rays. So X-rays are used to analyze crystal structure. Keep that in mind. Okay. Right? Sometimes in interviews also these questions will be asked. Okay, can we use this visible light to examine crystal structure? Impossible. Okay. Right, X-rays only can be used, and X-rays we cannot see. Okay, X-rays cannot cause vision in our eyes, so it is only by other techniques. Okay, indirectly we will go for crystal. We will understand the crystal structure. Okay, not by actually seeing atoms anywhere. Okay, now planar atomic density means it is like this. When I am sending a beam of X-rays onto a crystal. Okay, right? Now, in an atomic layer, crystals are having systematic arrangement of atoms or ions or molecules, you know. Okay, so atoms will be like this. Atoms will be like this. This is one plane containing atom. This plane is my imagination, that's all. Okay, only atoms are present. I'm imagining an atomic plane. Okay, imaginary atomic plane. Similarly, one more atomic plane will be like this. One more atomic plane will be like this. Okay, this is another plane containing atoms. This is one atomic plane, this is another parallel successive atomic plane. The distance between these two successive parallel atomic planes is known as interplanar distance d. That's what we have seen in Bragg's law. Okay, right? Interplanar distance d, like this, there will be 10 to the power 23 atoms. Imagine 10 to the power 23 atomic planes will be there. Okay, right? Now, you need not always consider the atomic plane like this also. I told you, you can consider atomic planes like this. In that case, what will happen? Interplanar distance, if a plane is like this is one atomic plane. The another atomic plane, this is another atomic plane. Okay, only difference between these planes and these planes is what? Okay, the interplanar distance d will be different here. Okay, you can visualize planes in any way. Okay, now I'll send a beam of X-rays like this. Okay, now I want to see, right, how many atoms will be there per square centimeter of this plane. Okay, per square centimeter of that plane, how many atoms will be there? Means what is the planar atomic density? We call it as planar atomic density. Okay, so how effectively, right, X-rays get scattered from different HKL planes can be understood if I know the planar atomic density. Okay, so and now we will go somewhat further deeper. Okay, it is like this. We have seen in a simple cubic unit cell, I am drawing only the front face. Imagine that it's a 3-dimensional figure. Okay, I'm not drawing the entire figure. Okay, right? We are seeing only one face of the cube. The cube is actually behind it. Now, this is one corner, this is another corner, this is another corner, this is another corner. One atom is present on the corner of every corner of the simple cube. So when atom is present at this point means what does that mean? The lattice point is present at this point means the atom is imagined to be like this. The center of the atom will be at that corner. Okay, and we have seen adjacent atoms touch each other. Okay, that's how we go for calculation. Okay, adjacent atoms should touch each other. Atoms are rigid spheres. Adjacent atoms should touch each other, and all atoms are of same size because carbon atoms are sorry, you take silver atoms or copper atoms or gold atoms. Okay, so one lattice point is here means right. The atom is expected to be like this. The atom will be like this. How we imagine. Similarly, there will be 4 more atoms, right, at the back face of the cube, such that all 8 atoms will be touching each other. Means, how do I visualize a simple cube? Right, you take 4 cricket balls, okay, arrange them in a square, touching each other, and take 4 more cricket balls and put exactly on the top of these 4 balls, such that there will be 8 cricket balls, all are touching each. Okay, well, adjacent atoms will be touching each other, and join their centers. You can imagine a simple cubic unit cell. Okay, in this picture, okay, this side, one face of the cube, we have seen one face of the cube is known as 100 plane. Okay, so what is 100 plane? Okay, it is one face of the cube. Okay, right, diagonal plane. Okay, diagonal plane passing through the body center is known as 110 plane. Okay, the plane passing through that triangular plane is known as 111 plane. What is 100 plane? Face of the cube is 100 plane. Now, in 100 plane, effectively how many atoms are present? If you see, 100 plane is effectively covering how much? How many atoms effectively? See, though this atom, right, is on this corner, entire atom is not getting covered by the 100 plane of this unit cell only. Okay, right, because the remaining area, only this part, 1/4 part of this atom's area is effectively coming into our unit cell. There will be one more unit cell to my left like this, one more unit cell on its top, and one more unit cell on the top of my unit cell. Means one atom's entire, what you call cross-sectional area. Okay, cross-sectional area of the atom is being actually covered by 4 atoms, 4 unit cells. Okay. Okay, it is a common atom for 4 unit cells. Okay, so 4 unit cells are sharing our atom's cross-sectional area. So effectively how much, okay, area is coming into our unit cell? Only 1/4 from this atom. Similarly, 1/4 only is coming from this atom. Remaining are shared by, right, remaining 3 unit cells like this. So effectively 1/4 of the atomic cross-sectional area, 1/4 of the atomic cross-sectional area, similarly 1/4 from this atom, 1/4 from this atom. So 4 1/4, effectively our unit cells 100 plane is covering only one atom's cross-sectional area. One atom's cross-sectional area. Okay, means the area of this 100 plane, Miller indices, okay, should always be indicated using common brackets. Okay. Those common brackets means Miller indices HKL. See, this nomenclature is important. Okay, notation. HKL are Miller indices, no doubt. If I use common brackets, right, it means that I am talking about Miller planes. If I use square brackets and put HKL in between them, I am talking about Miller directions. Similarly, if I put flower brackets, HKL in flower brackets, a family of planes. Okay. Angular brackets like this, family of directions like that. Okay, right? There are no different notations have different meanings. Because we are talking only about planes now, we use only common brackets. Okay, you cannot simply, brackets have meaning. Okay, brackets have meaning. Now, so our 100 plane of this unit cell is containing effectively one atom, covering one atom. Okay. Right, so what is the area of this 100 plane? If A is the lattice constant, what is the area of this 100 plane? A square area. A square area is covering effectively one atom. Okay, 1 square centimeter area will contain how many atoms? As usual. Okay, we proceed in the same way as before. Right, this much area is having effectively one atom, covering one atom's cross-sectional area. 1 square centimeter of that crystal will contain how many atoms? Okay, 1 square centimeter contains how many atoms? So, it is like this. Okay, right, 1 centimeter by A square into 1. Okay, 1 by A square into 1. Okay, it is A is equal to, suppose say lattice constant A equal to say 4 angstroms. Lattice constant A equal to 4 angstroms. In the case of CSCL, we have seen lattice constant A equal to 4.11 angstroms. So I'm taking a round figure 4 angstroms. Okay, so what is A square? Area of 100 plane will be 4 angstroms, means in centimeters it is 4 into 10 to the power minus 8 centimeters. Okay, A square will be 4 into 10 to the power minus 8 centimeters. Okay, so 1 by A square into 1 will give you number of atoms per unit area of 100 plane, because I have taken only 1 here. Okay, now, so we'll proceed like this. So effective number of atoms per unit area is 1 by 4 into 10 to the power minus 8 whole square. That's equal to 1 by 16 into 10 to the power minus 16. Okay, minus 16 goes up and becomes plus 16. Okay, so I'll take 100 into 10 to the power 14. Okay, by 16 I'll take 100 by 16, whatever it is. Okay, 425s are 4 4s are, it's around 6.25. 6.25 into 10 to the power 14 atoms per centimeter square. So in a simple cubic, okay, if you are talking about visualizing 100 planes, okay, 1 square centimeter of 100 plane, right, contains how many atoms, right? When I am sending an X-ray beam onto the plane of 100 atoms, okay, per square centimeter that X-ray beam encounters how many atoms? 6.25 into 10 to the power 14. That order is around 10 to the power 14, 10 to the power 15, 10 to the power 16, like that. Okay, planar atomic density we call it. Planar atomic density. Okay, now I'll proceed further. We'll go for into, right, say it's not only 100 plane, there are 110 plane, there are 111 planes also. Now I'll draw a perfect cube like this. Okay, we already talked about 100 plane. Okay, right? Now, say 100 plane is over. 100 plane I have talked about, right? In this area, effectively 4 atoms. So, though 4 atoms are visible, effectively this area is containing only 1 atom. So 1 square centimeter contains how many atoms? So lattice constant A equal to 4 angstroms. Okay, it is 6.25 into 10 to the power 14. Now this is not the only plane present in the cube, isn't it? Right? There are 110 planes, there are 111 planes, like that. What about 111 plane? 110 plane. Okay, 110 plane is like this. It's a diagonal plane. Okay, now this plane is also containing 1 atom here, 1 atom here. Okay, 1 atom here, 1 atom here. It's a simple cubic in itself. It's a simple cubic in itself. So, what is the area of this diagonal plane? What is the area of this diagonal plane? Area of the diagonal plane means length into breadth. Okay, so length is, so breadth is nothing but A, lattice constant A. When this is A, this is nothing but a phase diagonal. Okay, length of the phase diagonal V is root 2A. Root 2A. So what is the area of this diagonal plane? Root 2A square is the area of the diagonal plane. Area of 110 place. Not only 111, 110, it can be 101 or 011. Anything. Okay. 2 ones, 10, that's all. Okay. So root 2A square. Root 2A square area is effectively containing how many atoms? Now look at this atom. I told you when lattice point is here means the atom will be like this, the atom will be like this. Here also the atom will be like this, the atom will be like this. Okay. So here also if you look, right, into my unit cell, into our 110 plane, only 1/4 the atom is effectively coming, remaining 3/4 is being shared by other atoms, other unit cells, other planes, etc. So from this atom only 1/4 I am getting. From this atom also effectively our 110 plane is effectively covering only 1/4 of the cross section area of this atom. Okay, like this, 4 atoms are, right, giving only 1/4 into our plane. So effectively how many? Root 2A square area is effectively containing how many atoms? Root 2A square area is effectively containing 1 atom. Effectively containing 1 atom. So 1 square centimeter of 110 plane contains how many atoms? How many atoms? Now proceed as before. Okay, 1 by root 2 into A square is 4 into 10 to the power minus 8. I'm talking about centimeter square only. Okay, whole square into 1. That is nothing but planar atomic density. You simplify that. Okay, it is nothing but 1 by root 2 into 16 into, right, 10 to the power minus 16 goes up and becomes plus 16. Okay, plus 16, and you can write this as 100 into 10 to the power 14. Okay, nothing but 6.25 as before. 6.25 by root 2 into 10 to the power 14. You can further simplify that. Okay, atoms per centimeter square. Okay, atoms per centimeter square, planar atomic density. Okay, right, this is about 110 plane. Now, what about 111 planes? Okay, 111 planes in a cube are like this. Okay, so you take one cube again, cubic unit cell. Let it be simple cubic or BCC or FCC. Okay, right? Now, what is a 111 plane? 111 plane, we have seen if this is x-axis, this is y-axis, this is z-axis. Right? 111 plane will be like this, triangle. Look, appears triangular. Okay, so right, this is our 111 plane. Lattice constant is A angstroms. Okay, right, simple cubic means atoms are present only on the 8 corners. Atoms are present only on the 8 corners. Like this. Okay, right, now per square centimeter area of 111 planes, how many atoms will be there? Okay, it means 111 plane, right, covers how many atoms effectively? Okay, we want. Now, if an atom is like this, means atomic center is like this, means I told you again, atom is like this. Similarly, atom is here, this atom. This atom is not passing through this, our 111 plane is not containing this atom, but it is passing to this point. Okay, it is like this, and it is like this. Okay, this atom will not covered by our 111 plane. Similarly, the atom at the back corner also will not be covered by our 111 plane. Okay, our 111 plane effectively has only contact with the 3 atoms. What are they? This is our first atom, this is our second atom, this is our third atom. Okay, so what is the area of this 111 plane? What is the area of this 111 plane? Okay, what is the area of this 111 plane means it is an equilateral triangle, isn't it? This is one face diagonal. Okay, root 2a. Okay, this is also another face diagonal, left face diagonal. Its length is also root 2a. Its length, this one is back face diagonal. It is also root 2a. Okay, right, so this is an area of what you call, it's an equilateral triangle of side root 2a. Okay, what is area of an equilateral triangle? What is an area of an equilateral triangle? Just guess. Okay, a little bit of geometry knowledge is also required here. Okay, otherwise we have to calculate that half base into height, etc., etc. Okay, right, if you remember the area of an equilateral triangle, that problem solving becomes quick. Okay, whatever it is. This area is effectively containing how many atoms? I'll come back to that formula. Okay, this area, this much area is A. Let us call it as A. Area of this equilateral triangle, which is nothing but our 111 plane, is containing, is effectively covering how much area, cross-sectional area of atoms. Now look at this atom. Okay, this atom, this angle is 60 degrees only. No, in an equilateral triangle, this angle is 60 degrees. Whereas this entire atom's cross-sectional area covers 360 degrees. Okay, so only, right, 60 degrees atom is coming into our 111 plane. 111 plane is up to this point only. Okay, further, right, from here to here, it is not in our plane. It is not our 111 plane. Okay, so you have to exclude this area. Only this portion belongs to our unit cell, our 111 plane. Okay, how much portion is that? Okay, total area is covering 360 degrees. Our 111 plane is only cutting 60 degrees from it. Okay, means effectively only 1/6 of the area of this atom is coming into our unit cell. Okay, 1/6 of the atom is only getting actually covered. Similarly, here also this entire area is 360 degrees. Okay, in this our plane is only taking 60 degrees section. Okay, so from this also only 1/6 is coming. From this also only 1/6 is coming. Means 3 into 1/6. That is effectively half atom only. Means our 111 plane is effectively considering half atom's cross-sectional area only. Okay, so right, this much area, whatever area of this 111 plane is covering effectively one atom. Okay, so many angstroms or whatever it is. 1 square centimeter effectively contains how many atoms? How many atoms? Okay, that's how we will be proceeding. If it is what you call a face-centered cubic structure, what will happen? In face-centered cubic structure, right, additional lattice points will be present at the body centers, sorry, at face centers also. Okay, effectively present at the face centers also. Means the picture will be like this. This is again a unit cell. Okay, our 111 plane, our 111 plane is like this. Okay, now if you ask me to put atoms according to FCC structure, I'll put one atom here, I'll put one atom here, I'll put one atom here. At the face, top face center also, I'll put one more atom. Okay, let us put first on corners and then proceed. Okay, this is corner. Corner atoms are covered. Now, I'll go for what are known as face-centric atoms. One face-centric atom will be here. Okay, right face center atom will be here. Bottom face center atom will be here. Left face center atom will be here. Front face center atom will be here. Back face center atom will be at its center like this. 1, 2, 3, 4, 5, 6 additional lattice points will be present on the centers of each face. Okay. Now, we have what you call this 111 plane. Okay. Now, this 111 plane is what's called touching or crossing through how many atoms? It is obviously, it is having a part of this atom. Okay, 1/6 part we have already seen. Effectively, right, 1/6 part of this atom also. Effectively, 1/6 part of this atom also. Okay, moreover, our this bottom line, right, of this 111 plane is passing through a bottom face centric atom also. Okay, so if you imagine one atom will be like this. Okay, our area 111 plane is like this. Means effectively, okay, effectively, what is happening here? Right, this 111 plane is cutting this atom into two equal parts. Though I have not drawn it perfectly. Okay, means from this face centric atom, half of the atom is coming into our 111 plane. Similarly, right, it has nothing to do with what you call front face center. 111 plane will not touch front face center. 111 plane, right, is passing through this point. 111 plane is passing through this atom also, if you recollect it. Okay, right, left face center. One atom can be imagined to be like this. Our 111 plane is covering half the area of that atom. Similarly, it is passing through the back face. Okay, it is passing through the back face. Half of the back face centric atom also will come into our unit cell. Means half atom is covered here, half atom is covered here, half atom is covered here. Means 3 halves, how much? 3/2 atoms are coming into our 111 plane. Okay, and from these corner atoms 1/6, 1/6, 1/6. How much? Effectively only half atom. Effectively only half atom from this corner atom. From face centric atom, 3 halves, 3/2. So effectively, right, our 111 plane, right, our 111 plane, right, in FCC covers how many atoms? 2 atoms. Covers 2 atoms. Okay. So what is area of that √3a square by 4? Area of that what you call equilateral triangle 111 plane. That much area is containing effectively 2 atoms. 1 square centimeter of 111 plane contains how many atoms? As before. Okay, this is how we calculate planar atomic density. This information becomes very valuable for what you call crystallographers who are working in X-ray diffraction. Okay, so they'll understand what will be the intensity of the reflected X-rays, etc. can be understood easily if I know the idea of, right, per square centimeter the beam encounters how many atoms. Okay, right. So these two are important aspects. One is volume density, number of atoms per unit volume, and number of atoms in per specific planes, right, in per square centimeter or per square millimeter or per square meter. Okay, whatever it is. If it is square centimeter, angstrom is 10 to the power minus 8. If it is square meter, 10 to the power minus 10. If it's square millimeter, 10 to the power minus 7. That's all. Okay. Right? Next we'll cover in the next video. We'll see the next topic. Right? Thank you.